Okay, I suggest we get started. So Guillaume is a PhD student in the computational biology lab at the Duve Institute in Brussels. And his PhD focuses on identification of specifically single-cell proteomics data, because these mass spec data have specific characteristics, and maybe the tools that we use for bulk are not ideally suited for that. And as part of his research, he uses and develops packages that are focused on the identification of mass spectrometry data. And so that will be the topic of his workshop today. PSMatch is one of the packages, and he'll show, demonstrate, illustrate how to handle proteomics identification data with that.
Thank you, Laurent. So yeah, this workshop will be kind of a demonstration, more of a participation kind of thing. So you can follow along with what I show you. But if you want to load the workshop on your end, you can browse the vignettes. So to access the vignettes, you'll have to either install the package from the GitHub repo, Deflandre PSMatch Workshop, or from the Docker image. But I just heard that apparently you can also run the Docker image from the cloud of Bioconductor sites. I am not aware how you do that exactly. So if some of you are, don't hesitate to share it with the other ones that would like to do it. If you do it through this Docker image, you'd have to open your localhost 8787, and then the username is RStudio, and the password would be PSMatch. So maybe the show of hands who has already done it or would like to do it and would like some time to do it. Nice show of hands. So you'll have to browse the vignettes if you want to access the vignettes. But in any case, anything I'll be showing is available through the GitHub repo, and you can just follow along with what I show. Also, the R code that I'll be showing. So this is a well, everything I'll be showing to how you use PSMatch to handle identification data is also available on the GitHub repo. And finally, there are three main packages that I will be using throughout the workshop. They're called PSMatch, PTMods, and Spectra, PSMatch being the central core of this workshop, but PTMods and Spectra are also used throughout the package. These can be installed from BioC Manager, but the latest features aren't yet on the release page from Bioconductor, so you'd have to install it from the GitHub repo as well. And the GitHub repo is called R for Mass Spectrometry, PSMatch, and then there's a special branch you need to take. It's the @validate PSM. So if you could do that, unless you've got the Docker image, then everything's already installed for you. So maybe I'll leave some time for you to load anything you want or take a picture to be sure. And obviously I'm displaying here the three magnificent stickers we've got. Don't hesitate to... Ah, there you go. I know half of you come for the stickers. Freshly printed. All right. So the workshop, I'll first make a brief recap and introduction on mass spectrometry-based proteomics and particularly identification. And then I'll go into the core of PSMatch, how we can load your data, create the PSM objects, filtering the data and find the peptide-protein relationships through adjacency matrices. And then I'll go on with how to use PTMods and spectra to annotate spectra. And finally, I'll be ending the workshop with the newest features within PSMatch that include validating PSMs. So with a real show of hands, maybe, who is already familiar with mass spectrometry-based proteomics and maybe in particular identification? There you go. Oh, a bit of identification. I'm glad because I'll reel in more people into the dark side of identification in MS-based proteomics. So a typical bottom-up proteomics workflow would start with your sample. You've got your proteins. You digest them into peptides through the use of, for instance, trypsin. separate them by high-performance liquid chromatography, and then you would ionize these peptides before injection into the mass spectrometer. The mass spectrometer would then select first, create a first wave of MS1 spectra and select some ions from within this MS1 spectrum to generate the MS2 spectra. So the MS2 spectra contain fragments which kind of form the digital footprints of peptidoforms or peptides. So it's not proteoforms you identify, but it is peptidoforms. Proteoform groups are then later inferred based on the identified peptidoforms. So now we have generated our MS2 spectra, but how do we actually identify which peptides these spectra come from? So there are three main methods that we can use. De novo sequencing being the oldest one, for which we find a sequence based on its the peak mass differences within a MS2 spectrum. Then there's also spectral library searches, where we match previously already identified data with your observed novel data. And then the most used method might be the database searches, for which we match theoretical data with your observed data. The theoretical data being all the peptides your sample could contain. And so any of these three methods then generates a peptide spectrum match, so a PSM. A PSM ties an observed MS2 spectrum with a candidate peptide sequence. We're never really sure which peptide was really present in your sample, which is why it is a candidate peptide sequence. And you'll see how we have an idea of the confidence we have in these identifications through the false discovery rate estimations. So for every search engine output, regardless of its format mentioned here, well, you would record at minimum, obviously, the peptide the spectrum is matched to, the rank of that PSM, so its position based on the scored candidate peptides for the same spectrum, a spectrum ID, which can be the scan number or another spectrum identifier you can build on your own, the proteins that peptides stem from, a score given by the search engine, estimated FDR or false discovery rate based on that score, and then a decoy flag, whether the hit, the PSM, is a target or a decoy. So this last bit might be confusing, so I'll explain it a bit more in a bit more detail. So target decoy competition is often or preferably used through database searches, and instead of just taking a database with your target hits, so all the potential peptides you could find in your initial sample, you would generate a decoy database and concatenate these into one database. And this decoy is created by shuffling or reversing the initial target peptides. So instead of having, imagine KGR, Van der Eyck, Gatto, and Deflandre are the potential peptides that could be found in your sample, you would generate this second database, so double it, by reversing these peptides. And you know these decoys are false because they do not exist. These have been made up. And thanks to these decoys, you can have an idea of the false discovery rate of your identification. So based on the database, you apply your database search using a search engine, and you get for each MS2 spectrum, or at least you hope the most of your MS2 spectra, you get a best ranking PSM. So for instance, this score, 82 for peptide KGR, is attributed for one MS2 spectrum. And then for another MS2 spectrum, the best peptide or candidate peptide is Van der Eyck, etc., etc. And when you sort these scores, these PSMs by scores, you may have an idea of the false discovery rate. So you have one decoy for 5 peptides with 4 targets, and the estimation of the false discovery rate for a score above 64, or about 63 then, would be D over T, so 1/4. Now I will get to, I will get to explain how PSMatch and what PSMatch actually does. So who is PSMatch for? PSMatch is for proteomics practitioners who want to explore, filter, and annotate identification results after a search. So you have just run your search engine, and you want to import the results into R, filter your PSMs by low confidence hits, understand the peptide protein ambiguities, and visualize the matched spectra, annotated matched spectra. So PSMatch will not run a database by itself. It is applied after you've run the database yourself. And it won't replace your search engine scores, or not yet at least. And it also won't perform quantification. It's solely focused on identification. So to install the packages, you can, once they have been released on Bioconductor, you might use BioCMagic install, but for now you'll have to install through GitHub. So I showed this already, and let's load our packages. So for the example data I'll use throughout this workshop, I'll be using two datasets, one which is already bundled within the PSMatch package, and the other which is available through another Bioconductor package called MS Data Hub. The origin of those datasets isn't quite as important as what I show you what you can do with it. But if you want to know more, you can search on the MS Data Hub help pages. So both were acquired after a database search, so there was no de novo use or a library search, a spectral library search. Sorry. So you can load the data by calling data PSM bookway, and you can see that in this data set you have quite a few features, and I will come back to which ones were the most important. And then for the other one, I will call the MS Data Hub. There we go. All right. Now, PSMatch has a PSM constructor, so you would create a object of class PSM for which every row is one PSM, and the columns are the search engine output variables, so the ones I've shown here. And the key variables are those that are typically provided by the search engine and are found in an identification file. So I'm calling, first I'm creating a spectrum identifier because I want to make sure that every PSM has one spectrum identifier. I do this by using the file name and concatenating it with the scan number for that PSM. And then I'm creating the PSM object by calling my data frame and defining some key features that I mentioned before as well. So the spectrum identifier, the peptide that is matched by the search engine, the proteins that peptides stem from, whether it's a decoy or not, the rank, the given score, and finally the estimated false discovery rate. And so by calling this same object right away, you can see that you have 10,000 PSMs with 41 columns, which are these 40 plus 1 because I created the spectrum identifier. You have 10,000 unique spectra, so unique PSMs, for which you have all of the ranks that are of rank 1, and 8,000 are targets, and the rest are decoys. If you do the same for the other data sets, you can see that we have many less rows, 5,800, for which only 5,343 are unique, because you also have ranks that are higher. So you might have, for the same spectrum, different peptides, so PSMs with different ranks, and also a distribution of targets and decoys. So we can explore these PSM objects by simply calling the PSM, or you can load, store, and see the PSM variables that you have defined upon constructing the class using the PSM variables function. You can see that both variables are different for the two objects that I created, because those two objects come from a identification file from two different search engines. But the features are the same in the class as they are in the original data frame. So yeah, this is what I basically showed. So the file from the MS Data Hub, the ID object that I created is based on an MZID file, whereas the other one was based on a sage.tsv file. So the target decoy approach I already mentioned, where decoys are used to estimate the FDR, but other than that, decoys aren't quite as useful, biologically speaking, which is why we often filter these decoys out. But they do give a sense of how good the search engine performed. Normally, you should have your targets that are their distribution extends itself from the decoys. So using the target decoy package, which is yet another package, and I highly suggest using it to evaluate your target decoy distribution, you can see whether, loading the package first, you can see whether your distribution is correct. So in orange are your decoys, and in green are your target hits. And you see that normally the distribution, so the first peak of the B-model distribution for the target hits should match the distribution of the decoys as much as possible. Ideally, it should follow the curve along and then separate by the end, so that you have more target hits. So the false discovery rate is typically estimated using these decoys, and we often apply a filter around 1%, 5%, depending on the use cases. And so, for instance, the further away the second peak is, the more targets you would have. Here, the 1% would be around here, and so you'd get less peaks than if the distribution was further away. Go back here. So you can filter out these decoys by using the filter PSM decoy function. So remember, we have 10,000 rows for our PSM's object, and by using filter PSM decoys, we now have removed 1,823 decoy hits, and we have an object without the decoys. But then again, you can have multiple matches per spectrum. This was shown in the other identification file. So you can see that you had less unique spectra compared to the amount of PSMs within your object. You can do this by calling the spectrum ID. And you will see that we have up to 5 PSMs with the same spectrum ID. So let's find an example. This scan, the PSMs with this scan number all have different proteins, but all have the same spectrum ID and the same sequence. So this is typically an example of a peptide that is shared among different proteins. So one peptide that could have come from different proteins. And you can reduce your data for your PSM object, by using the reduce PSMs function. So reducing means that you would want to make sure that there's only one instance of a PSM with all the proteins stored within a vector in your spectrum ID. So I'm calling reduce PSMs. And now you see that where we used to have 5,802 rows or PSMs, we only have 5,343 now, because we now don't have any duplicated spectrum IDs. And for the same scan, we can fetch and see that the database access or the proteins are stored within a vector. And you can see if a PSM object is reduced by calling the reduced function. And so this then turns out to be true. So I already mentioned the shared peptides, so those peptides for which you have multiple proteins that could have, where the peptide could have stemmed from. But I will come back to these shared peptides in a minute. So first I want to show you how we filter the PSM data. So I already mentioned the decoy hits. We typically only use them to estimate the false discovery rate, and so you can filter those out using the filter PSM decoy function. But we also have filter functions for removing the PSMs for which the rank are bigger than 1, as those are typically the wrong peptides, as the biggest the highest score, the best ranking PSM is often the best candidate. We can also remove those shared peptides that create ambiguous protein assignments, so where you don't know which protein was actually present in your sample. And you can also filter by false discovery rate. As I said, depending on the use cases, you'd filter by FDR of 5% or 1%. And then we also have a wrapper that runs the three first filter functions, so the decoy hits, the ranks, and the shared peptides at once. So calling filter PSMs, which is the wrapper, you can remove all those. So you start with a certain amount of PSMs, remove all the decoy hits, remove PSMs with a rank above 1, and then remove those that are shared peptides. So peptides with multiple proteins. And so you're left with 2,666 PSMs. And to have an ID of those shared peptides, which is quite useful, we can use the describe peptides function. So yeah, this is an overview of the filtering functions. And so into protein ambiguity and adjacency matrices, to have an idea of which peptides are shared and how many are shared within your PSM object, use the describe peptides function. And you can see here that we had 9,254 peptides composed of unique peptides, 4,021, shared peptides among proteins. So you'd have 2 proteins, 3 proteins, 4, etc., up to 56. You'd have 2,642 peptides that were shared among 2 proteins. So you can see that quite a lot of those are have some kind of ambiguity. And you can do the same for describing the proteins, which takes a little bit more of time. There we go. So in total, you had inferred 11,000 proteins, and of which only unique peptides were stemmed from, were 2,200. And it basically gives you an idea of how your peptide and proteins are related within your PSM object. But this isn't quite the best way to have an idea of those peptide-protein relationships. The best way we found was by making adjacency matrices. So the make adjacency matrix function models those peptide-protein relationships in a sparse matrix. So the rows in the matrix are peptides and the columns are proteins. And then every entry is then bigger than 0 if the peptide was present or observed for that protein. The values in the matrix can be either binary, so either the peptide can stem from that protein or not, or it can be the count, so the number of PSMs for which that peptide could be found, or even in a weighted score, so the sum of the scores provided by the search engine for your PSM object. And so you do this by, so let's first filter by decoy and rank, as those aren't relevant in this context. And then you can build the adjacency matrix. So we're first filtering, removing some hits, and this is then an example of the first 10 peptide and proteins in our data frame. And if we make the adjacency matrix, we can see that our dimensions are 7,400 peptides for 8,200 proteins. And the 5 first rows and columns of this matrix, let's make this a bit bigger, shows you that the first peptide, for instance, was found in the first protein, the second one, but not in the remaining ones. And then this is the score provided, or the sum of scores provided by the search engine. If you remove the score, let's rebuild the matrix, but by removing the score with setting the parameter score to NA. We still have the same dimension, but now our adjacency matrix is just the counts of PSMs within our, the counts of peptides within our PSM objects. So you can see that we only had one peptide that was matched, one PSM that was matched to this peptide, and this peptide can only be found in these 2 first proteins. Now this is useful, but a matrix like that is actually huge, and you cannot possibly see all the relationships between your peptides and your proteins at once. So we use connected components. So we split this matrix into connected components, which then show us groups of peptides and proteins that share at least one link. You can call this by calling the connected components function. And there are 4 component types. So either there's a single protein and peptide that are linked. So this is the unique peptides, which is quite straightforward, basically. Then there are the well-identified proteins, so for which you only have one protein that is matched to multiple peptides. This just gives an increased confidence in the inferred protein. And then there are the shared or peptide ambiguities, for which you have multiple proteins for only one peptide. Those are the cases that are more tricky. And then there are the even more complex groups where you have multiple proteins and multiple peptides. I'm going to show you what this looks like. So calling the connected component function creates you an object of connected components. So this is a new matrix we have obtained, and the length of our connected components is still is quite big. So you can see that I've called, wait, let's, there we go. So we have our connected components. You have 1,050 of those that are 1 times 1, so one peptide, one protein. The same amount almost of one peptides for multiple proteins, quite a few less of multiple proteins for one peptide, and still quite a few for a more complex version where you have multiple peptides and multiple proteins. But you can obviously see only the matrices for those specific components that we have created. So for instance, this component shows that there's one peptide, one protein, this one for multiple peptides, one protein, one peptide, multiple proteins, and then the complex version. And you can also visualize these complex components. So here I'm checking which ones of the connected components have multiple peptides, so more than 2, as well as multiple proteins, more than 2. I'm just showing the header. And so if you take an example, so we're going to take 1,000, it's not in here. We take an example and we can plot the connected component. And you can see that in this case we have the proteins that are in the square boxes in blue and the peptides in orange. And if we had removed this peptide, you would have cut the connected components and created multiple other components where you'd only have this peptide for this protein, 2 peptides for this protein, and these proteins would have then disappeared. And this gives you an idea of connected components that are actually important, for which you have some peptides that connect all these proteins together, and once removed, actually split these connected components. To have an idea of which ones are important, you can use the prioritize connected components function, and this scores the connected components based on a few metrics. So let's do this. Up. And if you see the header of these metrics, so this gives you an ID, and row and cols means the number of peptides and the number of proteins, and then you have all these other metrics, so an idea of the sparsity of your matrix. These metrics that then are then used to have an idea of which connected components are the most important ones, and you can actually create a PCA on these to also have an idea which metrics are more how do you call it? Well, give an idea of which metrics give most variation within our data sets. And so, for instance, ncol and ncol, which is the amount of proteins, and nrow, which is the amount of peptides, are one of those bigger important metrics. And connected component 619, for instance, is kind of a outlier in this sense. Yeah. All right, so now I'll introduce PTMods, which is another package that handles modifications and especially how to annotate your sequences with modifications and maybe convert your annotations. So PTMs are those modifications that occur after translations, and the most common examples are, well, oxidation, phosphorylation, carbamidomethylation, or acetylation. And PTMs change the mass of a peptide and thus affects the precursor and fragment ion masses in the MS2 spectra. There are different annotation styles that are used by different search engines, and so PTMods handles a few of those styles. So there's the classic delta mass, where you add a certain mass on your sequence, which is used by a search engine called Sage, for instance. Then there's the Unimod ID style, where you have a particular ID for a particular mass or modification, which is kind of used by MSFragger. And then there's a more classic name style, which just shows you which modification is present, and this is used by MaxQuant, for instance. PTMods handles all three based on a data set from the unimod.org website. As you can convert your sequences into your preferred style using the convert annotation function. So for instance, suppose we have our sequence here that's called M peptide with an oxidation M, and you want to convert it to a delta mass. You can create your novel sequence where you have converted your annotation. You can do the same in between the other styles as well. But PTMods also allows to add fixed modifications or variable modifications. So fixed modifications are applied on every single residue of a single type. So for instance, we would typically apply carbamidomethylation on all cysteines. And so you can apply this using the add fixed modifications function. So once again, here we have a peptide scaled GR, and we call add fixed modifications, where we set the parameter fixed modifications to C carbamidomethyl. And now you can see that are all our cysteines are carbamidomethylated. But you can also apply a TMT label, so on the N terminus or on the C terminus by calling N term or C term. And you can obviously call multiple modifications at once. And so in this case, you still have your label as well as your carbamidomethylation. And then you can also call fixed modification on a position along your sequence. So here we only want to apply fluoro on our serine at the fourth residue of our sequence. So you call the pos parameter, and you suddenly add fluoro on your sequence. It just handles modification along your sequences, provided sequences. And then the variable modifications includes or not modifications along your sequence. So it's kind of the same, except you would generate all potential combinations that could exist within your sequence. So for this sequence and peptide, where we add variable modifications with a certain mass or a phospho on threonine, you would get all the potential peptides, so M peptide without any modifications, and with a delta mass, and pept with only the phospho, or both at once. Obviously, this explodes the amount of potential cases you could have, the more modifications you add, and the more residues that can be matched. So you can use the max mods parameter to set a maximum amount of modifications that can be applied at once, in which case you would only have 3 cases, so the canonical peptides, the peptide with the first modification and the peptide with the phospho, but not the one with both at once. And you can also strip your modifications by, so suppose you want to remove all modifications from a sequence, just call get canonical sequence, and then you get your canonical sequence. Pretty straightforward. All right, so the reason I briefly introduced ptmods was to introduce the other function in PSMatch that is more useful, is visualizing spectrum annotations. So PSMatch has a function that generates theoretical fragment ions. So these are those ions that are used through database search engines typically to match a spectrum with your theoretical peptides. So you match a spectrum that has fragment ions and compare it to all those ions that could have been generated by a precursor ion. And so all those ions include the B and Y ion series, which are the most typically used, but there are also the so there are A, B, C, X, Y, and Z ions that differ based on their fragmentation site. So to generate those fragments using PSMatch, you would call the calculate fragments function. And there are a few other parameters within this function that can define typically the charge states that you want, the different ion types that you want, and I'll show this right now. So let's load our spectra. So SP Buchweg is a spectra object, which basically has all the MS2 spectra loaded in it. I'm also creating a spectrum identifier, the same one I created for the PSM object. And I'm joining both so that both my spectra hold the spectra as well as the identifications. So calling the object then shows you how many spectra we have, 4,700, and each of those also now has a sequence. Sorry. But some of those spectra are MS1 spectra, which is why those don't have a sequence, which because we only identify the peptides for MS2 spectra. And if we get the spectra for a same precursor scan, we can now see that you have the MS1 spectrum without an identification and the MS2 spectrum, which has an identification. And so you can create your theoretical fragments using the calculate fragments function. Here we're taking the sequence for this spectrum object, which is the one I just showed above. And we don't apply carbamidomethylation. And now you can see that we have created this data frame for which we have all the MZ values for the different ion types. So from the B ions to the Y ions, but I could have set a parameter to call for more ion types. And we have the charges only set to 1. And those are all linked to a peptide. So you have this peptide with oxidation. And if you wanted to generate fragments with modifications, obviously PSMatch now supports modifications through the help of PTMods. And then, for instance, this small sequence where we have added a variable modification, you can also call, and now you have the theoretical fragments for both these sequences. So the MZ values for the peptide ATK or the peptide AT with phosphorylation. And now we can actually visualize spectra. So the usual plot in the spectra package is rather simple. So you only visualize your MS2 spectrum. You could also annotate this one, but using the plot spectra PTM function from PSMatch, you now have access to a clean view of which fragments within your sequence are actually matched. So in this sequence, we only have the B2 ion and all these Y ions that have been matched. In addition, you also get a delta MZ plot, which gives you an idea of how close the match between a peak and its theoretical peak is. So the delta MZ shows in ppm how close those matches were. So for instance, the Y8 ion has around 10 ppm between its theoretical matched ion and the observed ion. And so you can increase this tolerance by using the ppm argument. And now you can see that we have increased the amount of matches. So we used to only have the B2, but now we also have the B4, except the B4 has a huge delta MZ value, which indicates that it's probably not a good match. All right. So it's true that this plot spectra PTM function is also useful to compare identifications. So imagine you had this both these sequences. Wait. So you have your sequence here, well, this one you see at the bottom of the screen. You can also apply variable modifications or fixed modifications using the plot spectra PTM function. And so here we call oxidation through the plot spectra PTM function, which calls then the PTMods variable modifications functions. And so in this case, we see that our sequence with oxidation and without oxidation shows a clear difference in amount of peaks actually identified. So the one with the modification shows more peaks, where this one will basically shows only those that don't include the modification. So this helps decide which one. So this was obviously a very easy and clear example, but when you have multiple PSMs for which you're unsure which one is actually the good identification, you can visually compare those, and this gives an idea of which one is actually a better identification. And this leads us to the following section, which is the validating PSMs, where we try to validate whether a PSM is actually correctly identified or not. So validate PSMs add per PSM spectral and identification metrics that are currently not supported by your typical search engines. And I'm not going to go through all of the metrics, but I'm going to show you one. So you have the main function. So here I'm first taking all the spectra that have a sequence in them, and I'm filtering by precursor scan based on these. And now I can apply the validate PSM function, and this creates a data frame with the spectrum identifier for every PSM that was in your object that was called. It's scanned so that you can also easily reattach it to the original data frame, and then the peptide that was matched, and it gives you the FDR that was matched, that was linked to it. And then finally, the metrics that are used are the presence of the A2, B2 ions, the presence of X2, Y2 ions that are typically a good indicator of a good fragmentation of a peptide. The BY overlap that I will explain in a minute. The shift consistency, so if there is a modification, how many, what's the percentage of fragments that could include a modification that are actually matched by your PSM. Whether the parent ion intensity is high or not. So typically you should have a very low parent ion intensity. Otherwise, it's an indicator that the precursor ion wasn't properly fragmented. And then also the precursor purity, which shows kind of a similar metric where the fragments are based on only one precursor ion, or if multiple precursors were fragmented together. And so you can add these metrics by matching them with their spectrum ID or scan number. And so the one metric that I quite like is the BY overlap, and I'm going to show you how it's relevant. So this plot shows you a spectrum for which you only have the B ions 2 and 5 and the Y ions 3, 2, and 1. And so you notice that there's this huge gap between the B ions and the Y ions. And this is an actual identification obtained, and you would wonder how can we be so sure that this is a good identification, because we barely have a few fragments that have been matched. And so BY overlap kind of tells you, look, there's a gap between your fragments, and your Y ions don't overlap your B ions, which means we're not really sure that these, sorry, yeah. It's true you would go further. I think the BY overlap metric also has a stringer delta MZ value. So this one then is matched according to plot spectra PGM, but not according to the metric. And so, yeah, this kind of rings a bell telling you, hey, we have some serines here. Should we not try to apply phosphorylation and see if you suddenly get more matched peaks? So it's kind of a metric that can be used as an alarm bell or ring bell when you've run a search engine with a few modifications. but you might want to try some other ones. And there's a new feature that I want to add as well, is to try, basically try your luck. So you use check overlap, checking if there's an overlap or not. If there isn't, then you apply well-known modifications on your sequence, and if you get a better match, then it's an indicator of, hey, maybe you should try this modification that we found on your data with a search engine. Yes. No. So PSMatch for now isn't. You do get an idea with the precursor purity whether the initial peptide was well selected for fragmentation, or if a larger window caused for multiple precursor ions to be selected for fragmentation. But further than that, and you still have like one identification per PSM. So for your PSM, you have only one peptide, so you'd only match those theoretical fragments for that peptide. This is, yeah. No, phosphor is a name given by the Unimod. Oh no, you mean for this? Where is it? You could, and I mentioned phosphor. I have absolutely no clue if that would actually be helpful. I think serines, right? Yeah. Now it generates all the combinations because I applied the variable modifications, and because we had how many? Yeah, we had 3, 4 serines, which is why it generates 16 spectra. And so if might be complex to do this. Let's instead do paste this one. And just add here. Now how should I apply it? Indeed. And I don't remember what the first spectrum was. So we have the B2, B5, and then Y5321. So we do get more identifications using phosphorylation. So more matched peaks, sorry. Yeah. Although those also have quite a large delta MZ value. But it doesn't really show, there's still a gap, and I'm not quite sure how much these identifications are better. But it does ring a bell telling you that there might be a missed modification that you haven't included, and you might want to reapply a search engine with these modifications. And there you go. This was the workshop for PSMatch. I hope you were able to follow along, and if you have questions, don't hesitate to ask them. Thank you. I am very much limited to identification, so I've only worked on identification, and for quantification, I'm not